Anthony,
Hey, David, how are you?
pretty good. Long time no see. Haven't seen you in a while.
Yeah, haven't been on SIPI call in a while. How's it going?
Um, Going okay, moving along slowly. So,
Planning on using this for the demo for the VRM stuff, the voltage regulators
um,
for
yes,
power integrity.
that that would be nice.
Okay.
Yeah, just need to get a little bit more solid definition, and then we will apply it.
Okay.
Let's see how the attendance goes. Let's give everybody a couple of minutes.
Yeah.
Actually, it's
I do have interest in the 24/16 stuff. There seems to be some general interest in some of our divisions where we may want to consider that for some apps for developing, but I want to make
okay.
sure we,
Yeah, we should talk about this offline.
yes, I agree.
Yeah.
Yeah, okay.
Yeah. Um, I guess on the let me let me say a few words about the SIPI kit. What has been going on?
Okay.
Uh, so there was there's interesting side discussion going on about what does it mean for two chiplets to be compatible and to talk to each other. Right. I just attended this morning the link layer meeting, and that has a little bit of implications for us in terms of how we define things in the SIPI kit.
Okay.
That said, this is what I write, and specifically what is a PHY and what is interface, right? And what is a link, right? So I think
All right. I know what a PHY and an interface is. What do you mean by link?
so. A PHY, if you take SerDes, right? If you take by 16 SerDes,
Yeah,
right?
the PHY is a SerDes. That's the physical interface, right?
Right.
So that's just the
But
electronics that are transmitting and receiving the data, right?
right. So
The interface, you're meaning the channel that connects
n-
the
no, no,
device.
no, no. So let me
Okay.
backtrack a little bit.
Okay.
When you think about a SerDes, right? Say a by 16 SerDes,
Hmm.
okay? Now a physical link is actually only one of the lanes. That's a probably lane is a better word, right? We have one lane,
Hmm.
uh, right, and then a PHY will be comprised of uh, 16 lanes. Now the interface realistically is defined by the link layer that sits on top of it, right? You may have PHY that is by 16. But if the link layer treats it all by fours, you technically have 4 by 4. Link layer could treat it as 1 by 16, right?
Hmm.
So in that respect, interface is kind of defined, at least in my mind, by the link layer. Interface is what you connect, right? If you have on one side an interface that is by 16, and it's the link layer treats it as a one interface. On the other side, you must have a by 16 interface to talk to it, right? Because the link layer on the other side is also going to treat it as one interface, right? The link layer is going to do all the ordering and synchronization of data and splitting of the data and things
Yeah.
like that between the different lanes.
So conceptually, the link interface defines the logical interface, and the PHY is the physical wires that are used for that interface.
Yes.
Yeah.
If you take, for example, UCAE, UCAE has one data TX lane, one data RX lane. And
Yep.
similarly, it has one sideband data TX and one sideband data RX. So
Mm-hmm.
UCE is going to have 4 lanes. And then the interface is going to be the combination of those 4 lanes. Right? Because I need to take that whole interface.
So a lane is the atomic level interface.
Yes.
Yeah.
Yes. Right. Basically, so in that respect, thinking about
So
SAPI
one
kit,
lane has effectively, I guess, two RX, two RX, two transmitters, two receivers, and a clock, for the front and back channels.
actually each
Or
one
separate
of these
clocks.
is going to have its own clock.
All right. So
Right.
there's two clocks and two sets of transceivers. So the back lane is totally independent of the front from a logical
The
perspective, but they share the
the
same wiring.
sideband, yeah,
Okay, got it.
right. So actually, uh, let me backtrack a little bit. When talking about in this UCE example, this one UCE which has 4 lanes, that is going to look like one PHY.
Mm-hmm.
However, there could be a link layer on top that takes 2 PHYs and makes it into one interface.
Mm-hmm.
Right. So when we are talking about the SAPI kit, what we are going to be applying and specifying parameters for is going to be the atomic PHY. Each TX, each RX
Yep.
gets its own definition. Then we're going to take that and say, hey, you know what? These set of 4 comprise one PHY. So if you want to check if you want to do SI analysis between PHYs, right, you need to consider all 4 at the same time, right? Or all lanes inside that PHY at the same time, right? Sending data back and forth, sideband communication, and so on.
So a channel is one or more lanes, right?
Yes.
And it goes up to how many? Is there a max, or I mean, you can have multiple PHYs, right? So is it truly?
The interface in terms of link layer then is going to have multiple PHYs, right? And those
But is there a max number of lanes for one channel? Is what I'm asking.
max number of lanes per one, no. Those are going to be defined by whatever the standard is, right? If you think about
I know, but the standard I think does have an upper limit, if I'm not mistaken. I believe it does.
Oh yeah. If we're talking specifically in the context of UCAE, it has 2 basically one high speed TX, one high speed RX, and then 2 low speed sideband TX and RX. That's it.
Yeah.
Uh,
Yeah, but the UCAE spec is configurable, and there's there's a finite number of configurations that are part of the spec.
That's right.
Right.
Yeah. Now, the way to this same approach can be applied to HBM, right? HBM, each channel is going to have each, right? Actually, channel is the meaning within the HBM standard, right? HBM4 has 32 channels. These 32 channels, each channel is going to have its own T-axis, R-axis, data, strobes, sideband, and so on, right? And
But
redundancy.
HBM is not configurable, right? It's fixed. There's HBM 1, 2, 3, 4, but I don't think the four.
It's not configurable. Yeah. But we are going to define it as all these 32 channels then become one interface that must be connected to one interface on the other side. Right?
Yep.
So that's the high level kind of terminology and structuring of the different pieces.
Okay.
Where that becomes important is in determining the compatibility of chiplets. We can, right from SIPI perspective, we can look at the per lane compatibility, right? And determine, hey, this lane with that lane is compatible, is going to work, right? If you have PCIe, on one side it supports Gen 5 and 6, on the other side it supports only Gen 6, you would know that, okay, I cannot communicate Gen 5, or, right? Stupid example, but
The
kind of,
ESI analysis would be done at the lane level, right?
yes.
Okay.
At the lane level, and probably actually,
And there's multiple lanes in a channel, so really you want
yeah,
to look at the worst case lane, but in theory you need to check every lane, right?
that's right.
Yeah. But,
But
but typically the way people really do it is, through symmetry, all your lanes, you may have 16 lanes that are all part of one fire, one interface, and it's the same transceivers on either side of the interface, or
that's right.
yeah. Well,
Yeah,
certainly within the chip, you don't have to use it, but generally you don't mix them within the chip. But
yeah.
I've actually done that in a previous life. But
Yeah, I guess
so from an analysis perspective,
today,
you're
yeah,
kind
yeah,
of wasting your effort. I mean, if you know what the worst case channel is, that's probably the only one you have to. And if you know they're all replicated, the channels, you just have to do one analysis, right? So if you're if you have a channel and you're using it hierarchically, you could just analyze one channel and
yeah,
you don't have
yeah,
to analyze every one. But if you're doing full custom, then you got to look at every wire, right?
yeah, yeah.
But oftentimes, the way these things are structured, it's not fully symmetric. So you may have three
Yeah,
unique channels that are in multiple instantiated. So
that's right.
yeah.
Yeah,
But that
and
I don't know if there's anything provisions in our formats that say these are the unique channels of concern that where you could tag it to save you some work. Because normally, yeah, an SI engineer, there's some a prior knowledge from the design teams that would kind of know that, but there's
yeah, I
when
think,
AI starts doing this, that that needs to be defined or
yeah,
articulated.
yeah, I think from chiplet vendors' perspective, that they deliver that description, it will be difficult to identify which channel, which lanes, which channels are important, right? They don't know, they don't have any visibility
Yeah.
at the upper level integration. So I think we are still going to be depending on the integrator persona
Yes. Yeah.
to figure out,
Oh, absolutely. Absolutely.
yeah, right? Yeah,
Yes. Yes. Because that's the configure. How you configure it will determine
yeah,
and how you build it. Actually, it's not just the configuration, but it's the implementation as well.
yeah, yeah. So yeah, that's kind of what um, has been going on. And then that follows a little bit into the kind of structure of the SI kit where we describe a lane, what the lane is, and give parameter for the lane, and then we describe what a phi is, and then next level is we define what an interface is. And I was just talking this morning to the link layer folks, and especially with FCSA ARMS definition that came out, to be able to describe what link layer is being used and in what profile, what different profiles it supports, right? Because it can be configured differently depending on what you're doing. And a chiplet kind of has a choice to support or not support some of the profiles. So it's a basic description, kind of the way I understood it is list of profiles and versions for those profiles so that we keep track. And then next level up
So
is
in layman's terms, I mean, these are basically, standardized high-speed interfaces that are have multiple channels, but the formatting of the data is really kind of the link layer, right? Which is logically having
yes,
information,
yeah,
and
yeah,
there are different protocols on how the data gets presented, packed and unpacked,
exactly.
and all that belong.
Yeah,
And
ECC,
there's
size
maybe
size of
different.
ECC, the flit, the ordering, all that weird stuff, right?
Right. And I suspect those different, I like to call them protocols. I don't know if that's the right term, but each protocols, I guess in general, might have different um, signal integrity requirements, right?
Um, I
Or
don't think so.
no. So that
Uh,
so that's standard, the loss, the speed, the all those eye diagram specs and stuff, you're saying that is standard, independent of the link,
if you're thinking
independent of the
protocols
protocol. So,
like Ethernet versus PCIe,
mhm.
those are different PHYs altogether. Those are different electrical
Right,
protocols,
right, right. But
right?
UTI is intended to be a universal PHY and it supports multiple protocols. So the question is, are the specifications for that channel the same for all protocols?
Yes.
Okay. All right.
Yeah, it's the PHY has to support the PHY link. The physical link has to support that signal integrity, regardless of what is the data that runs through it.
Okay. So it's strictly kind of logically how the data is, presented
Right.
to device, but the channel
Yeah.
itself, that's their specs. That's a standard spec, and you need to meet those
Yeah.
specs. Okay.
Yeah. And that I don't think at this time we want to go down the route of adding the additional logical protocols that sit on top of those interfaces.
I
I think
agree. I agree.
we'll leave that for the
That's
next iteration.
Yep.
But I think it's important at this time we kind of capture a structure of the SIPI kit that is amenable to extending it for the next level definition.
Okay. So I guess the the way I recall what we're doing here is you've got a chiplet. That chiplet will have a phi, and we're asking the chiplet providers to provide the is it this SI
Yeah.
certain information that is used in the analysis. So, I mean, typically you're providing an IBIS model to represent the physical structures, but that's just the specific electrical characteristics of the transistors that are transmitting the data.
Yes.
But the specs per se, um, if it's tied to a specific PHY, you say, or HBM in our case, those specs are predefined. So what information are we asking the chiplet provider to provide from that
What
perspective?
we the way the idea is the specs are predefined, but they're somewhere in a paper format, right, in the standard.
Yes.
What we are asking, what we want to have is all those specs to be put in a file
Okay. So
so that as a
essentially, we
simulation.
want to have an electronic version of that spec, and that
Yes,
could be part of the JetX standard. And when you create, it's really the electrical model, right? That would be the E101,
yes,
or a branch of that, a
yeah,
subtree. That's where it goes, right? It's in the electrical
yes,
schema. We should have kind of those. We already have the physical predefined pin names, right?
yes, yep,
And essentially, we want to have the predefined specifications at for that lane, right?
yes,
Okay. Okay.
yeah,
So that's pretty straightforward. So
yes.
do we have those specs captured in the schema?
No, not yet. We don't have the schema yet. So we just have a list of parameters at this point. But
Okay.
the schema is going to come in next. The idea with this approach is, yes, you have the standards. Define some standards define limits, right? You see, for example, who define the limits,
Right.
which is great, but
Right.
on the other hand, it leaves the door open for what is the actual fight doing, right? So
Exactly. So
basically,
it may exceed the limits.
it
It
may be
may,
much better than the limits,
but
right?
in theory, it could be less than the limits. So, it's, but if you want to buy a cheaper one where you don't need the full specs, I suppose that's an option. But I would think, most any IP vendor that's serious would provide meet the minimum requirements. But
Yes,
I think in general,
but many may be better, right?
right. But do
Allowing,
we want to also offer the ability to find less if they're not achieving the spec?
we will let if um, the way I'm thinking about this is let people describe their IPs and FIs and not necessarily tell them, well, if it's less than that, don't describe it, right? I
Well,
don't know. It doesn't make sense to have less right, something that doesn't meet the standard specification. But
you're saying that, but it could. When I'm thinking that from a practical perspective, I agree. An IP vendor would probably be
yeah,
stupid to offer a PHY that doesn't meet the specs.
it
But when
yeah, it
you
doesn't make sense,
but
right?
when you integrate a PHY into a chiplet, you know, you may be degrading, the way you've laid it out, you may have done something where you're compromising the overall integrity of that interface, on how you whatever.
Supposedly, even after integration, uh, that chiplet should still meet the limits, right? I think the interesting,
It should.
yeah, I
Yeah.
think the interesting piece
But
here is
let me
when,
just finish my thought. So
okay,
at the end of the day, a chiplet designer is going to design a chiplet. They're going to integrate a PHY, and they're going to get the parts packaged, and they're going to test them. And they'll have some kind of loop back test that specifies they're meeting the specs or exceeding the specs, right? So so they may decide they want to do binning, right? So they maybe there's high performance, super high performance, just meeting, and maybe they rather than throwing the parts out, they can sell them for half the price and say this one is 90% compliant with the spec, 10% less, but if you can use it, we could sell those to you.
Yeah.
So I don't think we should prevent
Yeah.
the
I
chip.
don't think so either.
Yeah.
Yeah.
Okay.
To me, the interesting situation is where the PHY and the chiplet end up better than the standard. Because as an integrator, to me, that is more interesting because it gives me more margin to work with at the integration level.
Mm-hmm. Mm-hmm.
Right. And I would like to know that even if I'm simulating against the standard, I would still like to understand what my margin looks like.
Yes, exactly. Exactly.
Right.
So yeah. So
Yeah.
so the way I view it at the pure, early stages of an architectural design, you're just dealing with ideal specs because there are no files, right? So
That's
you
right.
have ideal files and they are the spec. This is it. And at some point, you're going to start doing technology mapping and you're going to be picking IP vendors from a catalog. And it's going to be offered in different processes, right? So you're going to pick a technology specific, vendor specific PHY, and the idea is in the JEP 30 model. Uh, that's what we're hoping, that chiplet vendors will code up their IP and put that in the catalog, right? They can pick and choose, and they can say, all right, this is the cheapest PHY. It meets the spec. But for this my particular design, I've got some big ugly channel, and I can't really, I need some margin in the PHYs, and
Yes.
it's probably more on the receive side that is where you get it, because I've actually done designs with some high performance network, tier one networking
Yeah.
companies where we had our PHYs, and not all PHYs are equal. So Avago had kind of at the time the best SerDes on the planet, and that could basically, as long as it could accommodate crappier channels and crappier PHYs, and it was more forgiving of
Yeah.
channels. And so we not only need to look at the transmit side, but the receive side, right?
Yes.
To
Yep.
understand how tolerant they are of both channel and transmitter
Yeah.
performance. So I think from that perspective, that would be useful for a system designer in their IP selection, to have the ability to, and it's probably more cost optimization, right? Because most people are worried
Yes.
about costs, right? So if you're
Yeah.
cost conscious, you're gonna, maybe I don't buy that, super high end SerDes. I can live with, a tier two, which is not as good, but it's good enough for my design.
That's right.
Yep.
Yep.
Okay. Okay. And are we, so that makes sense now. What else are we doing in this spec? Is that pretty much it? Just providing
Yeah.
provisions to provide the
Yes. Yep.
okay. Now what about the channel itself?
The channel itself is not so there is the channel itself, there's two the from UCE perspective, UCE defines a requirement for the channel.
Yes.
So the way we deal with the channel part is if a PHY or an interface have specific channel requirements,
Yes.
we'll put those in the spec, right? And those are insertion loss, return loss at different frequencies and
Well,
so on,
when you
right?
say
That's
we put
basically
them
that
in,
curve.
yeah. So when you're defining your spec, there's a channel. So essentially, you're just attaching a property or however we're doing it, saying this channel needs to meet this spec, which is in a machine readable format.
Yeah. Basically,
And if you're
yeah,
running signal integrity on that analysis, you don't have to read the spec, or you just get the requirements and run the analysis.
exactly. Exactly.
Yeah.
If the standard does not come with um, channel requirements, we just won't put them.
Okay.
For example, the way Bo dealt with that, they left a budget on the for the channel, right?
Oh,
Which you
okay. So from the same argument we had, again, my particular system is low performance, and I don't necessarily, maybe I'm going to run it at a slower speed, and I can relax my spec, so I can override those channel requirements if my requirements are less, or maybe I want to over constrain. So
yeah
we're providing the default specs in there, and then the user, the chiplet provider can override their specific what they have, and the designer of their system can also override their channel requirements, either make them more stringent or less stringent.
yeah
Okay, got it. So we just introduced a new product. It's called Protocol Analyzer. Have you heard of that?
no
So we've had it for several years. For the PCB. So all of the standard SerDes interfaces, kind of what I call chip to chip, not die to die. Um, but it runs strictly on the channel. So if you're laying out a PC board, it has all the specifications captured in the tool itself, and then it will actually check those interfaces that they're compliant. And
okay
it's automated. So we've just recently added a UCIe compliance checker. So that's our first, and we'll be offering HBM as well.
okay
So so that's something that we could have. Um, but it's just checking to the spec. So I think again, we're offering with this format the ability to either relax or further constrain those requirements, if
yes
sorry, rather than just saying you need to meet or exceed this.
yeah exactly
Yeah, and I don't know if our tool allows you to add extra margin or stuff that that may be already available in the tools, and I don't know what our you know competitors are doing in that space. Do you?
I don't know.
Yeah. So from uh yeah, so from the channel perspective, I know we've got a product that just kind of checks to make sure you're meeting the spec. I don't think they have anything specifically for the defining. So this really, I don't think, is part of the implementation tools. I think the value here is more in the system definition tools.
Yeah.
Yeah. Okay. So yeah. So and those. So if that's where you would define the requirements at the system level, and then those requirements should be pushed down. So if you have more or less stringent specifications, that should be defined in your spec, and then it should be we should have the ability where it can we can support that in the implementation side.
Yep.
All right. Um, yeah, I'll talk to some of our system guys to see if they're interested in that. We should also talk to Michael Durkin to see if he's open to. Have we had has Michael been involved in any of these discussions?
Which Michael? Durkin?
Michael Durkin. Michael Durkin.
Um, so I worked with Michael Durkin to get the test design kit 1.0 into JEP 30. So that's done. He has not been involved following the
So
SIPI kit,
so
but
so
once
he
we get to schema definition, we'll
okay.
definitely work with him.
Okay.
I know JEDEC has some, JEP 30 has something about interfaces.
Hmm.
So we'll need to make sure that that
Right.
basically that gets upgraded to meet
Okay.
these.
All right. So he's got it. So it's gotten approved and they've added it to the spec.
TDK 1.0. Test
Yeah.
design kit, not SIPI. We
And
are not.
then they'll chew on that and decide if we need to reformat or change stuff.
Yeah.
Yeah, we should probably go through that exercise before we implement.
Yeah.
Okay. Uh, we've been, uh, I mean, have we been promoting this publicly at conferences and stuff?
Which piece?
What do
The
we,
SIP.
what are we calling this?
This is the SIPI kit. We don't have it published yet, or we don't have a schema definition. We just so far gotten to capture the parameters and define kind of how we are going to be applying these parameters to which parts. Next order is to put a little bit more meat around the XML. Um, show some examples how
How
this
about
would
we
look.
call it an SPK? Well,
Um,
no, well, I guess IPK.
yeah.
We could call it PIK, a power, yeah, PS,
Well, I think we'll keep on calling it SIPI kit.
SIPK. Okay.
People understand that.
Yeah, yeah. Okay.
It's no need to abbreviate it to abbreviate SIPI anymore, right? Um, it's already abbreviated.
Yeah, yeah. I like the three, but three letters is kind of limiting.
Yes.
We've used most of the combinations, but
Yes.
okay. So we're calling it an SIPI design.
Yeah. Yep. And we'll see if in the future we come up with a shorter name, we can always change it.
Yeah. All right. So again, back to my question: have we been presenting this, at conferences and stuff, or has anyone?
So in October, I did present the overall work and did talk a little bit about the test design kit and what was the other kit this was another kit that we updated.
Okay.
So yeah, I have
Any
been I
any
have been pro
interest? Do we get and anybody come up after say, hey, this looks pretty cool, or
yeah, that whole discussion around chiplet compatibility, where the intersection point is with the SIPI kit. So the SIPI kit has the opportunity to be a little bit more, right, than just straightforward electrical definition.
yeah, I'm sure those committees are gonna. This is pretty straightforward stuff. It's all those protocol stuff that gets really messy and security,
Yes,
and I think that's getting beyond our scope, right? So I think
yes, yes,
we want to stay
yep,
away from that. Just keep this
yes,
at the interface level.
yeah, yeah.
Um, okay, so I uh, I did AJ, I don't know if you know AJ. He runs the EBS division. Michael
Yes.
Durkin's boss's boss. So he's the general manager of the system package division.
Okay.
They make all the PCB tools and the packaging tools, hyperlinks, all those tools. So at our last, management review meeting last month, he did mention that they're considering, support
Um,
JEP
Tony,
JEP 30.
Tony, this a
Yeah,
recorded call, right?
yeah,
Okay.
yeah. But I'm just saying, in general, Siemens is open to supporting the JEP 30.
Okay, good.
Yeah, I just want to let you know that in general.
Oh, nice.
Yeah. So I think we're interested in including that as part of this. Have
Awesome.
have any other EDA vendors expressed any interest that you're aware of in adopting the standard?
I don't know. I don't know.
Okay. Yeah, I don't know either.
Yeah.
Yeah. Okay. All right. Very good.
Yeah.
So anything else?
No,
All right.
that's all. I think that's all. And anyway, it was just two of us, so we had a good chat.
Yep. Very good. All
We'll,
right. Thanks,
we'll,
David.
yeah. Thanks, Tony.
Bye.
Bye.